Welcome to this section, chapter 16, where we're going to look at circular motion and very specifically in this, the use of radians. So hopefully you've covered radians in maths before now, so none of this should be a surprise, but now is probably the first time that you're going to understand why we're so enthusiastic about radians, because it is here in this physics that we first find the very good application of that angle measuring system. Let us talk about how we describe an angle in a circle. The ancient Babylonian mathematicians were the very first people whose writing we still have, and so whose ideas we understand. They divided the circle up into 360 degrees, which we still do today. One of the most obvious reasons for this is just the very large number of factors that 360 has. We can divide 360 in half, we can divide it into quarters, into thirds, into all sorts of things, into 36, into endless number, including 360. So it's very, very useful. It's also very similar to the number of days in a year, and so you can see how dividing it up by that seems to be the most sensible thing to do. However, what we are going to do is we're going to leave that system behind and we're going to start measuring things in radians. And you might ask, well, why? Well, hopefully by this point you would have covered radians in mathematics, but here's a little bit of a thing. Roger Coates, a contemporary of Isaac Newton in 1722, he posthumously published the book Harmonia Mensurarum, and within this he spoke about comparing the circumference or an arc length to the radius of a circle. So his thinking was, and though he never used the word radian, I mean that came much later by James Thomson, which was Lord Kelvin's brother. The idea of the radian has its origins in how circles are constructed. We know that the relationship, and we've known this since the time of Archimedes, the relationship between the circumference and the diameter of a circle, that ratio is pi. So pi d equals the circumference, or 2 pi r equals the circumference. Now think about that just for a second. Imagine the circumference is the arc length and you can go all the way around this circle. Well, what is the magic number that links the circumference to the radius? It's 2 pi. If we divided up the circumference of a circle by 2 pi, then it would be made up of sections equal in length to the radius. And this is where the radian comes from. It is an angle that forms when the arc length is equal to the radius, and we get 2 pi of them around the circle. And so we have to do this translation in our head that 180 degrees is pi radians, and we'd probably express that 90 degrees was pi over 2. We start to describe it in fractions for mathematical purity. Now we're going to use this radians from now on, so we've got to get used to it, but this is basically the idea of where it has come from. If we're going to talk about circles, it might be useful to make sure that we always understand the same meaning of a word that we're going to use. So therefore, it's correct to use defined words, words defined in mathematics, to describe parts of a circle, so that we're always talking about the same thing. Now, we're not going to use all of these, but here are some that you might find quite curious. Like if you were eating a pizza, for example, and you take what you would call a slice, or a slice of cake, for example, where it's a line that is, I suppose, running at 90 degrees to the edge of the cake, goes to the center, and then it comes out somewhere else. You know what a pizza slice is. Well, in mathematics, we call this a sector. And if you had a small slice, and it's the minor sector, and the remaining rest of the pizza is the major sector, unless, of course, you're really greedy and you choose for yourself the major sector. Some things don't divide like that. If you've ever had a poppadom with an Indian meal, for example, you break it, you find that a crack will form through the poppadom, kind of at random, almost at where you flex it. And so a poppadom divides into segments. A minor segment is the bit you've got in your hand, and the major segment is the bit that you put down. If I was to look at the circumferences of the minor segment or even the major segment, then I could call those arc. The arc length of the minor segment is called the minor arc, and the arc length of the major segment is called the major arc. Now, if you go into books of geometry and go all the way back to Euclid's Elements, there are words used and defined to describe certain lines drawn in relation to a circle. And the first that we want to talk about is diameter. It comes from the Greek joining of the words dia and metron, a diametron, and it basically means to measure across the circle. I mean, how good is that? Now, the other words we use, that radius, means spoke in Latin, so it's from the center to the edge, and tangent, which is also Latin. It means a touching line, and a tangent, just behind my head in this video, it's a line that is basically at right angles to the radius at all times. These are the words we're going to use to describe circles. It's really important that we always use the correct terminology. Angles are really important when we describe the motion of an object going around in a circle. For example, if we thought about the International Space Station, it has a linear speed that's really high. And by linear, I mean, if it was going in a straight line past me right now, what rate would it be covering those meters? Well, every single second, it would be covering 7,822 meters. 7.8 kilometers. That is rapid, but you need to be rapid to stop yourself from falling out of the sky. And so an orbital speed, a linear speed, is really great. It means that you can actually circle the Earth about once every 90 minutes. But that means you're going through 360 degrees, or alternatively 2 pi radians, in 90 minutes. It means in any given second, you're only traveling through a very, very small part of a radian. The actual angle through which you have turned is really small. And so it almost seems like a contradiction. You could have a very high linear speed, but a very low angular speed. And of course, the thing that makes the difference is the radius of this circle. The space station is a long way up, as measured from the center of its rotation, which is the center of the Earth. It's the radius of the Earth is about 6.4 thousand kilometers, and the space station about 300 kilometers further on than that still. It's a huge radius. And so therefore, to cover that ginormous circumference, even traveling rapidly, it's not going to go through the angle very quickly. Whereas a merry-go-round in a park, its linear speed is going to be much lower because its radius is smaller, but its angular speed is going to be quite high. It's going to turn through that angle quite rapidly because it's a small object and it can just turn in a reasonable time. So what's the definition then of angular speed? I'm talking about the rate at which I'm turning through an angle, the rate at which I'm covering that 2 pi of that circle. Dividing by time is basically telling me what angle I have moved through every single second. That's the way to think about it. We use some symbols to represent this. We use the lowercase omega to represent the linear speed. We use theta to represent the angle that has been turned through, and we sometimes use theta when we're drawing triangles and find angle theta. So theta represents angle in most cases, divided by time, lowercase t. So here it is. I want you to notice the similarity between normal speed. Speed is measured as the distance per unit time, and this is the angle per unit time. So you need to think that angular speed is very similar. It is an analog of linear speed, and the formula looks the same. Now, since we're working in radians, this is where the magic starts to happen. If we imagine a distance or a displacement travelled around a circuit, and I think it's better to say distance really, because as you go in a curve, you're not going to continue with the same direction all the time. You can change direction as you go. So the distance is linked to the radius if you measure it in radians, because we know that the arc length is equal to the radius when the angle is equal to 1. So look at this. If I had that situation, if the angle was equal to 1, then the arc length s would equal the radius r. That comes from the definition. But it means that no matter what we do, if we double the radius, then we're going to double the arc length. You can see that if we multiply either side of this formula by a factor, it will end up multiplying the other side by the same. That's how these equalities work. And so that's really useful. We can always work out how far around the circumference of the circle an object has travelled if we know the radius and the angle in radians that it's turned through. And we can also go one step further as well, because what we can do is we can look at the regular definition of velocity. Velocity is the distance travelled per unit time. Yes, I know for the purists out there we'd say displacement per unit time, but bear with me. Now, what we have defined the distance around this arc to be as equal to r theta. So if we substitute that into our formula, then we get the velocity is equal to r theta, which is equal to the arc length divided by time. But notice how in this formula now, we've got theta divided by time. We, in the last slide, defined that to be the angular speed. It means that we can find the relationship between the linear speed and the angular speed. And guess what? The constant of proportionality between the two is the radius. And so therefore, I have to take my linear speed, divide it by the radius to give me my angular speed. That's why the linear speed of the space station was so high when its angular speed was so low, because the radius was so high. So why are we obsessed with angular speed and not really angular velocity? Well, remember that velocity is a vector quantity and it indicates direction. As you're moving around a circle, your direction is always changing. So if you had an angular velocity equivalent to a linear velocity, it would be constantly moving. So it's not really that useful to describe an angular velocity. An angular acceleration, yes, but not an angular velocity. There are some places that choose to use the words angular velocity to describe the orientation of the rotation. Like if it's clockwise, then it would be a positive angular velocity, and if it's a negative movement, it would be negative. But of course, this is totally dependent on the observer's point of view. If you look down on planet Earth, it's rotating one way. If you look up on planet Earth, it's rotating the other way. And what you find is that measurement, angular velocity, doesn't measure anything about the real world other than your particular observation of it. And so for that reason, we just tend to ignore the term angular velocity. It's not helpful. But there are lots of places where this is really helpful, because particles in magnetic fields go around in circles, these devices called cyclotrons. Those ginormous particle colliders, like the Large Hadron Collider, they all work because the particles are following the physics of circular motion. Of course, it wasn't that led to the discovery of these formula. Isaac Newton, writing them down in the Principia, he was looking very much at the movement of the moon in the sky, explaining its orbit around the Earth as a result of a force pulling it towards it, but having too much sideways velocity to fall straight down. When we try to calculate the orbital movements of spacecraft and moons and planets, we have to consider the equations of circular motion. Up to this point, we've really looked at very small arc lengths, like of 1 radian. But of course, in the real world, things don't just go 1 radian and stop. The moon doesn't just go that far and fall out of the sky. It in fact goes round and round and round. So we need some terminology that's going to help us to describe motion that's periodic, where basically the arc length is larger than a circumference. And we actually have this terminology. We have actually defined some quantities to describe things that are repetitive in the waves topic. So for example, we had the period of one whole rotation or one whole cycle of a wave. And we're going to use that too, capital T, to represent a very specific time period measured in seconds. And of course, the reciprocal of the time period is the frequency. And the relationship is frequency is 1 over time period, and that's simply because we define frequency as how many things have happened in 1 second. And if it was in a different amount of seconds, then the 1 in this relationship would be a different number. So we're going to use these frequency and period within our formula to help us to create some equations that are useful to us, that we can substitute values in that we might have actually measured. Now bear with me while we work towards a new equation here. You're used to the idea that, basically speaking, velocity is displacement over time. Now I'm here I'm going to just call displacement d. You can see there's a complete lack of consistency with what we're calling distance and displacement in this. And it's because it's always distance when we're talking about going around in a circle rather than displacement. But however, we would normally not describe velocity as being distance divided by time. But just bear with me, I'm trying to get somewhere here. Normally, velocity is distance divided by time. Now, if we're talking about one whole rotation, then what we're talking about is distance divided by the time period t. So that would be d divided by capital T. And what we know capital T to be equal to is 1 over f. Now, distance divided by 1 over f is the same as distance times f. So there we have it. If we were going round in a circle, then we're talking about how far, like around we were going, then we would have this expression that the velocity was equal to the distance we travelled multiplied by the frequency through which we were doing that same distance. Okay, so pause with me there. Now consider this. If we were talking about the distance in angle that we'd gone around, by referring to it as frequency, we're talking about going around the whole circle. And that angle is 2 pi. So if the distance in angle format was 2 pi radians, then we would have this different relationship. We would say that not the velocity, but the angular speed was equal to the distance we travelled through in angle terms, 2 pi, multiplied by the frequency. Omega equals 2 pi f. We call this not just the angular speed as we defined it before, but because this is in terms of the frequency, we sometimes call this the angular frequency. When would you use one over the other? If you're given angles, you'd use omega is theta over t. If you're given frequency, you'd use omega equals 2 pi f. Choose your weapon based on the information that's given in the question. So if we have the angular frequency, omega equals 2 pi f, then what we realise is that we can substitute back in t. If we know the time period instead of the frequency, because we know frequency is 1 over time period, we can define that the angular frequency is equal to 2 pi divided by the time period. So 2 pi over t. Very useful formula indeed. And with this, if you know how long something takes to rotate once, you can work out the angular frequency. Like, and here's the little challenge to you, can you work out the angular frequency of the 3 hands of a clock? You know one goes around in 60 seconds. That is the second hand. You know the minute hand goes around in 60 times 60 seconds, 3,600. I'll leave it to you to work out how long it takes for the hour hand to go round once.